All right, so we're going to talk a little bit today about rotational kinematics. Now, rotational kinematics are just like regular kinematics. They work the same, except everything's angular. There's an angular version of position, there's an angular version of speed, there's an angular version of acceleration, and so it's all going to be the same. So if you guys remember back to math class, you'll know that the equation for S, which is arc length, can be found using the angle that you've traveled times the radius that you're going in for a circle. So this is going to be for a situation when you have a circle and I want to know how far I have gone when I have gone an angle like so with a radius there. So it's going to be like that. All right. So this is the basics for all of them. So the RS is our arc length. So that is our distance. Let's make that over there. Our theta is our angle, right? And R is radius. These are all things you guys should know. So this is just your basic way of converting from angular stuff to linear stuff. So this is, linear distance here. Let's put linear below it. Okay. That's going to be the major gist. So in converting anything from angular stuff to linear stuff, I really just need to multiply by R. Done. That's it. Call it good. For example, let's do another one. If I wanted to do something like, say, convert from linear speed and angular speed, I could use this formula, where this guy right here is going to be your linear speed. Your V, your omega, which kind of looks like a W, is your angular speed, and R is, as always, your radius. So when we convert from angular speed to linear speed, we just multiply by R. If I want to go back the other way and find angular speed from linear speed, I would then need to say, well, omega is V over R. And that's pretty much it for linear speed. So we can do, let's just go to a new page. We'll do angular acceleration real quick. So if I want to do go from linear acceleration and angular acceleration, it's the same exact thing. So linear acceleration is A, angular acceleration is alpha, and R is, as always, your radius, right? So there's another formula you have. And that's it. So all of these are the same formula. Why are they all the same formula? Well, if I want to go for linear stuff, let's consider that. If I have, position, how do I find speed from position? Well, I would say V is equal to your change in position over your change in time, right? So if I now wanted to go to angular speed, I could say, well, angular speed is omega, which is V over R, right? So I can do that. So I can now just divide that by R, but then I have delta X over here. X is position. What do I get when I divide position? Or maybe in this case I could call it arc length. Let's call it that. Delta S over delta T. Like that. And what do I get when I have your arc length divided by your radius? Well, if we look at our other formula, we had delta S over R Now this is going to be r and t, right? Is going to be equal to, going off the side. And we know that delta s over r delta t is just going to be, well, this term here is omega, right? Well, is speed. So that's going to be v over r, which we just said above was equal to omega. There we go. So, I mean, yeah, that's about it so far. So now the big change we need to make from here is that all of our linear kinematics equations have a rotational equivalent. So the basics, if we start with the basics, we can say position is equal to velocity, constant velocity times time, right? Plus your starting position. Well, if I can do the same thing with angles. I can take this same formula, and now I can write it as theta is equal to omega naught for your constant angular speed plus your initial angle, right? That's it. I've just divided the whole equation by r. So what are our other equations that we have for linear kinematics? Well, I could say, basically take the same equation for speed and say this is going to be v equals constant speed times time plus initial speed. All right, so I can do the same thing. I can say your angular speed is equal to, that's supposed to be an alpha. Let's write this a new line. Omega equals alpha naught times t plus omega naught, your initial angular speed. All right? That's pretty much it. And let's do the other ones. Okay, so the next one I have is x equals 1/2 a t squared plus v naught t plus x naught. If I divide that whole equation by r, each term, I've got x over r is going to be theta, a over r is alpha, v over r is omega, x over r is theta. So I'm going to say theta is equal to 1/2 alpha t squared plus omega naught t plus theta naught. And our last equation we have v final squared is equal to v initial squared plus 2 times a times delta x. Right? Let's extend this guy. Divide the whole equation. Well, I can't divide just by r. In this case, I have to divide by r squared because I want to get this v into omega, right? V omega squared, from v squared to omega squared. So I have to divide both sides by r squared, which works out because I'm going to divide this one by r and this one by r. So I can convert this to alpha and this to theta. So we're going to get omega final squared is equal to omega initial squared plus 2 alpha delta theta. And that is all for have to know for this. Now you just use these like you would any regular kinematic equation. The big ones we're really going to need to focus on, though, remember, are going to be this guy and this guy. These other ones down here are useful, but we're going to use them less commonly than these first two. All right, guys, I'll see you in the next video.